Happy New Year, everyone. Welcome to 2022. Today's speaker is Marcelo Moretti, who is an assistant professor at Oregon State University. Marcelo did his undergraduate work in Brazil and his graduate work in California. The graduate work in California focused on herbicide-resistant mare's tail and hairy fleabane. Today he's going to talk to us about managing herbicide-resistant weeds using electricity. And here I have to admit that I've always been a bit squeamish about electricity, so I'm really curious to hear about the safety aspect of this technology if Marcelo talks about it. Marcelo, it's all yours.
Thank you, Matt. Let me make sure everything's working fine. Can you see my presentation? Is it on presentation mode now?
It is.
So it's my pleasure to be here talking about this work that's funded by USDA Crop Protection Pest Management. And I'm not going to cover too much on electricity safety to humans. I'll just make some comments of what we learned as we were assembling the equipment. And why am I still working on herbicide resistance, even though I moved from California to Oregon? Well, this is a nationwide, or basically a global wide problem on resistance. So really fast forwarding to just the tree nuts, or mostly hazelnuts, we have some similarities between hazelnuts and almonds or walnuts you see in California. We're mostly located in a valley. Here we are in the Willamette Valley. It's about 1 million acres, if I'm not mistaken, between the Cascade Range and the Coastal Range. And within this area, that's where we have Portland, Salem, Eugene, among other cities. It's a highly populated area. And our hazelnuts are grown conventionally. Here's a nice picture of what an orchard looks like. Flat soil, no debris, mostly no cover crops, because we are harvesting the nuts from the ground, just like we do with almonds and walnuts. One big difference you see at the base of the plants, you see a lot of foliage. Those are the suckers. Hazelnuts are meant to be a bush, but we train them as a single stem. There's a lot of effort going to that. And because we're growing those conventionally, to this date, herbicides are the main and only method of weed control we have. And no surprise, as we simplify management of any pest, we start to have resistance. And to this date, I think we have 5 or 6 resistance to 5 or 6 different modes of actions in the state. Not all of those are in hazelnuts. Some of those are in the annual cropping system. But for the herbicides that we do use in hazelnuts, we're seeing resistance to all of the post-emergence herbicides. Here's an example, a few pictures I've taken since it started, where you see escapes after paraquat application, fairly high rate of paraquat, and basically looks as good as the non-treated, which is not shown on the slide. And to your right, it's another site where the grower had sprayed glufosinate in the entire orchard. And I come back 2 weeks later, and this is how it looks like. It looks like a lawn. So the resistance is a big problem, because these plants, they really thrive here in Oregon because of the moisture and the type of climate we have. They will grow fairly tall. I would say 3 feet tall is not hard to see this ryegrass in orchards. And the only available option, if not using herbicides, or like in this case where the herbicides were used but fail to control the weeds, is mowing. But mowing is not effective way of killing ryegrass. You just suppress the top. You may reduce seed production, but it would require so many applications or operations in a season that becomes unbearable. At the end of the day, the growers still have to do the other activities of production and not just managing weeds. So it's fairly clear that we need a non-chemical weed control system that's compatible with this no-till system that we have in tree nut crops. We cannot use tillage because we're harvesting the nuts from the ground, and mowing, which is almost the only other option, is not effective. So that's why started looking into other alternatives. I've done some work on steam before, and since 2020, I've jumped into electric weed control. So I'm saying this is a rediscovery of the technology because it's been around for a while. I found this citation in the late 1800s. It was the first patent. And the commercial units in the US were around since the 70s, maybe 60s. And that specific company is still around. I think they renamed, but the basic concept of that implement is still available. But that application is mostly meant to go over annual crops or crops of smaller stature, not in orchards. You see a very large boom that could be 40, 50 foot wide and being placed just above the canopy of your crop. And the weeds that are growing taller than the crop will touch that electrode, close the circuit, and electricity will move down, heat that plant, and kill it. So problems with that system is first, it requires a very large tractor. We're talking about 200 horsepower plus to power that size of unit. And the size of the unit itself is not compatible with the orchards we have. And in this case, I'm saying that's where the safety to operators were concerned. You could not be standing nearby a running equipment like that when in operation, because there's no control where the electricity is going. Electricity is basically going where it closes the circuit. When there are no plants touching it, you just start having some like lightning effects going anywhere, and it could be the person standing nearby. So the safety concerns and cost at the time basically put this technology in the second plan. This is always the gold age of the herbicides, right? Eventually, we end up having these herbicide tolerant crops, and fast forward to this day, now we're going back to this because of resistance, among other issues. So this recent push, I would say in maybe last 10 years, maybe more, we're seeing a lot of companies, globally speaking, investing on electricity, mostly for weed control. I think there are other uses as well for pest management in general, for nematodes, I'm aware. And here are three that I've been communicating with. First one is ZASA, which is the unit I end up buying. You'll see in a moment. It's now they are in partnership with the Massey Ferguson partner company, parent company, I believe is AGCO. So they're going widely in Europe, in Latin America, and I've been told they're coming to the US. They have multiple units. Some are for roadsides, industrial use. Some are for ag, and they have one that's specifically for horticulture, perennial horticultural crops. As you can see, the size of the applicator in the front is about 5 to 8 foot wide. It extends a little bit, and the electrodes at this time are touching the ground. So the picture in the bottom is from Woodwave. Woodwave has a commercial unit, which is the picture on the top, where they have equipment for spot treatment. So we would control specific weeds here and there as you're moving with a truck or a UTV. And they were also developing a tractor mounted unit that you show on the picture in the bottom right, where you can see electrodes and a generator in the front. And these would be non-selectively killing all the plants that are in contact with the electrodes. And these are always in contact with the soil. So the safety to humans is much higher because you have a direct flow of electricity. Very unlikely you see a lightning going into this stand, a person is standing next to it. And the last one is crop zone, which is a similar idea as the first one we were talking about, which is large areas, row crops. But at this time, they're applying a solution to the foliage of the weeds to improve conductivity of electricity. And in this case, the electrodes are touching the crop. So it's like for total kill, for a pre-plant type of weed control, at least the unit that I'm aware of. These are based, CropZone is based in Germany, Rootwave in the UK, and Zaso, it's kind of global. They have Europe, South America, and I believe they're coming to the US as well. So I've been talking about how electricity killing plants, but how does it work? And if Steve Fenimore is online, he's going to dispute me that. I call this a thermal weed control method. You call it a physical weed control method. And the reason why I'm calling it a thermal weed control is because this high voltage electrode will touch the foliage of the plant, and then a current will pass through the plant. And that electric resistivity or resistance on the plant will convert that energy into heat, and therefore killing the plant. And there are some equations that were developed by that. Initially, they were saying that the energy required to kill a plant is related to the voltage. That's why high voltage, the contact time, and also the plant resistance, which I switch over to plant conductivity. It's because I'm trying to kill resistant weeds with electrical resistance would be a little bit confusing, but the idea is the higher the plant conductivity, the less energy it would take to kill that specific plant. And now this is the unit or a similar unit to the one I have, which is again tractor mounted. The picture on the top right, you see it's using the PTO from the tractor. So the tractor uses our energy source connected to a generator, which is that blue portion towards the bottom of the implement. And the generator would be coupled to a transformer. So that's the time when you increase your voltage at the cost of amperage to deliver high voltage to the electrodes. There are some controllers on the back, and those are connected to wires towards your electrodes. They could be mounted on the back, they could be mounted on the front. In this case, we have a front mounted, and those are basically 2 sets of metal fingers to close the electrical circuit with the soil and the plants in between. The applicators could vary in shape and size, but usually they are basically dictated by the size of your generator. So for this manufacturer, a 30 kVA generator, which is the one shown in the picture, will be able to treat about 4 feet at a time. And they also have a 60 kVA, which will treat 8 feet at a time. There's some correlation in there. So the important part is the electricity will move through the plant because it's touching the plant, and depending on the application, is actually touching the ground as well. And then we'll close that circuit here between plant and soil, and then and move back to the second electrode. So the key part is not only the equipment setup will play a role on the efficacy of this application, but also the target plant and the soil conditions. Before I jump into each of those factors, I want to show it in action because I've been talking about something that you probably never seen. I think there is a sound associated with this video. It's just a tractor sound, no one talking. So if you hear a tractor sound, this is why. You can see here I guess I shut off the sound, at least for me. Maybe you're not hearing me. So this is one of the applications that we're doing at very low speed to promote the highest rate of electricity that we can possibly do. And you're seeing that the electrodes here are always touching the ground. And when it closes the circuit in some instances, you see a lot of sparks. It's because we are operating at high energy. So fire hazard is a concern. But a person, according to the manufacturer, could be standing about 6 foot away from the application. This is just the tractor driving, so I think I switched the slide. Here is another idea why I call this a thermal image. So it's an inexpensive thermal camera, which I apologize is not going to give you resolution on what temperature precisely we're talking about. But the red color means higher temperature. You can see as we are driving the vegetation, different location from the previous picture. You can see that as I'm driving, I'm hitting out that stretch of weeds to a color similar to the one in the engine. Has, of course, not that as hot as the tractor engine, but it is heating the plant. So what factors will affect this electric weed control? Well, first, the plant species. Plant species on the sense of morphology. The ones that will have a better contact will likely be easier to control because you're just having a longer contact time or a larger contact surface. I suspect composition as well, because those plants will have different conductivity of electricity. Lower conductivity for some reason has a different composition, is not moving electricity as far. It's not going to be as susceptible. And also the morphology, that electricity will have to move down the soil and into the other electrode. So the root morphology is likely involved on that efficacy. So something that has one taproot would have a clear pathway to continue transporting electricity. And things like grasses that have multiple roots may not have a uniform distribution of electricity within the root. The stage of development, no surprise, younger plants are much more sensitive to any treatment, and we're seeing that across the species. Water status, we need water in the plant in order to have a good conductivity of electricity. So plants that are severely stressed may not be as sensitive to electrical treatment. And then the composition, going back to morphology, perhaps composition, woody tissue. Well, wood is actually a good insulator for electricity. So woody tissue, no surprise, does not move electricity as well as herbaceous tissues, and we're seeing that in some weeds. And again, the plant density, the more plants you have in a given area in contact with electrode, and the more pathways for you to distribute that energy. So you would lose efficacy. The more plants you have, the larger the plants are. Some indication also on roots, going back to roots, there's indication on crop safety at least that roots, sugar beet tubers at least, they're more sensitive to damage, secondary damage from electricity than something that doesn't have as much of a large root system. It could be the moisture content, it could be the shape itself. It's a little bit unclear to me at this point. How about the soil? Well, soil resistance or impedance or resistivity, there are quite a few terms out there. I like better the resistivity. The soil resistivity will have a huge role. The idea is that we would like the soil to be less conducting for the electricity, so the electricity will stay longer in the plant. And what affects that? Well, mineral composition, texture, and moisture. The picture on the right, I forgot to put the source, is showing that soils with high clay content have a much lower resistivity, or in this case, conductivity, high conductivity, they are reciprocal, than some sandy soils. So ideal conditions for you to improve efficacy of this technology is to have lighter soils like sandy soils. The moisture is also, more moisture content will improve the dissipation of electricity in the soil and basically serve as a groundwater, literally. So you want to have dry soils for better efficacy. And warm soils tend to have lower resistivity, which combined to all those things, I think California is a much better scenario for electric weed control than Oregon, for instance. We are often cooler, moisture, and heavier soils than some of the places I've been in the valley, Central Valley, I'm sorry. So with all that in mind, there's no reports on whether this technology is compatible with hazelnuts or not. And even the basics is that efficacious for controlling weeds. And in this case, we're going after the resistant ryegrass. Forgot to mention, but most of our populations now have some sort of resistance. There's like about 70% of those are resistant to glyphosate, 80 or more resistant to group 1 herbicide. So there's a collection. Also, the other important information is crop safety. We are applying electricity to the soil, which should protect the plant. But in specific cases of hazelnuts, they have those suckers that I showed in the first picture. Yes, we can remove those ahead of time, but at one point in time, there might be a direct exposure. So we need to know, is it safe or is it not a good idea? And eventually, is it cost effective? You know, killing weeds is not hard, it's just expensive. You can always pull it by hand, but at what cost? And we're looking for something that we can do in large areas. economically. So a little bit about the methods. The first one, I'm basically trying to determine what speed can I really recommend this implement to control weeds. And we had 2 trials in 2021. It took us a little bit of time to get up to speed because setting up a new implement during the pandemic was a challenge. We learned how to assemble this over Zoom, and when you're playing with high voltage, you're sometimes scared. And all the time we're using that Zasso 30 kilowatt implement that's tractor mounted. It requires a 75 horsepower tractor. We end up using a 105 horsepower tractor because our soils are on the heavier side. We realized that 75 horsepower wasn't really giving us enough power to operate the equipment properly. And those 2 locations were severely infested by ryegrass. In one case, they were escaping glyphosate, the other case is escaping group 1 herbicide. Our plots were about 2 foot wide, which is the size of our applicator, slightly longer than that, wider than that, and 40 foot long. And we had a uniform and natural infestation of ryegrass. In this case here, the grower mowed everything but the strip of grasses that we were going to treat. I won't talk much about all the analysis that we or parameters we're measuring, but just wanted to let you know we're trying multiple speeds, different voltages, and looking into not only the density but the coverage of the ground by these weeds, and looking at the reproductive output from ryegrass, so inflorescence size. A second study is a crop safety study, which we planted 2 varieties, 2 important hazelnut varieties here for us. It was McDonald and Webster. And those were planted in 2020, just a few months before we started the trial. And we're looking at worst case scenario, what would happen if we apply multiple times a season, just this electric weed control. And at each application time, we would have 2 electric energy rates, which we're doing it by changing the speed either a 1/4 mile an hour, which is the video I showed you before, or 1.25 mile an hour, which was based on the previous study to give us an idea if a high rate would be more damaging to the plant. We are also doing it with or without suckers, just in case to show that the presence of suckers, which would be in season, would be negative to the crop. We're comparing that to a weed-free standard and also cultivation. There are many aspects we're measuring: tree growth, trunk caliper, photosynthesis rate, and eventually yield. We hope to conduct that for at least 3 years. If I can, I would like to continue for longer. And both of those studies are being used to collect data for our estimates of costs. So I haven't done that part yet. So a little bit on results on the efficacy. Once you apply electricity, you will start to notice a change of color. This is just an area we're testing. Within 45 minutes, sometimes even less than that, you see a darker color where the electrode pass. It's fairly fast. 2 days later, this is the Canby site. We're seeing a lot more necrosis and some indications of regrowth in larger plants. And this is a week later. So about a week later is when I see complete necrosis. And from there, you either see plants recovering or this is what the treatment will do. Just a comparison, on a large plot scale, I have my non-treated on my left. You can see a strip of green grass. It's a week after initial treatment, and a close-up of the weeds. They're doing fine. Vegetative stage, they were about 1 foot tall or even less at the time we treated. And to your right, you can see my high voltage, low speed, and you see a nice strip of dead grass going 40 foot or more down the road. And the closer picture, you can see where the dead grasses are compared to the edge of the field. Little quantitative data on what we have so far. This is all done as a single pass. So we pick a point when the grower would be either mowing or spraying. And then we did at night either 9,000 volts, which was the highest voltage that we could sustain treatment with the tractor, or 5,000 volts. In each of these voltage settings, we had 5 speeds: a quarter mile, half a mile, 1, 2, or 3 miles. As you can see here, 9,000 volts, quarter mile, all the way to 9,000 volts to 3 miles. So what I'm showing here is the biomass, average biomass from all these 4 replicates, and we separated the shoots from the inflorescence. This is dry biomass. So you can see here the non-treated, how big it would be per square meter. And a quarter mile here, significant reduction. It's about 10-fold, not quite there, but really close. And we're reducing the shoots and the inflorescence. And from there all the way to 2 miles an hour, there's no really statistical difference on this treatment. That variability is because it's a natural population. And as we jump to 3 miles an hour, then we see a reduction in efficacy, fairly clear. So at a higher voltage, this is the highest voltage I could sustain, but the equipment is rated all the way to 12,000 volts. So it could be perhaps even faster depending on the tractor. We're seeing that 2 miles an hour will give us effective control. I'll switching over, looking at the lower voltage here. Nothing as good as the high voltage, but from quarter mile to a mile an hour, fairly similar results. And then it jumps up at 2 and 3 miles. Why would you go lower voltage when you have to? At the time of the year when soil moisture is greater, you will have to reduce your voltage, so you're not imposing as much load on your engine. Even though you have 105 horsepower, there are days we cannot operate because the soil conductivity is probably so high that we cannot sustain electricity. So the generator is demanding too much from the tractor, and that could either kill the tractor engine or damage our transformer, which is working too much, so it would heat up and be damaged. So those are the times we stop. We're seeing that lower voltage is less effective, but at the same time, up to a mile an hour, which is somewhat comparable to mowing, I would say. But in both cases, looking at the inflorescence biomass, which is the red color here, we are reducing flower production. I don't have viability of the seeds because this is a commercial orchard, and after 40 days or so, I'm forced out of the field. But we would like to continue with more controlled studies this year to see, okay, what are we doing on seed production and viability, which is the end goal, is to control or eliminate seed production. So we have the benefits of ryegrass as a cover crop, and we're able to kill it when it's not needed anymore. How about other weeds? I've been talking about ryegrass because that's the one I'm going after, but there were other weeds on our way, and not to the point that I can collect reliable data at this time, but sometimes a picture tells you a lot. Yellow nutsedge was severely damaged by electric weed control, multiple rates, Canada thistle as well, and field bindweed. That's a Canada thistle towards the bottom and a yellow nutsedge to the right. We saw that the most sensitive weed so far has been horsetail. So horsetail was fairly tall, and most of the times we applied. Here's a picture where you can kind of see a pathway right in the middle of the picture to your right. A lot of dead grass next to green areas. That was in our testing here at the research farm. We had a solid patch of horsetail, and we managed to kill it, but the clover was coming back down below. And that was a high speed, maybe 4 miles an hour and really low voltage. And horsetail, for some reason, is very sensitive. And there were the weeds that were less affected. In contrast to that, in a case where we're going low speed, high voltage, we did not really kill Himalayan blackberry. So you see damage. It's not that it's totally not affected, but that damage is restricted to the top. You see regrowth. And I think that's because the electricity is just not moving. This picture is showing here the untreated on the left and the treated on the right. You can see on the top here, that's where the direct the electrode probably made most contact, so I can see a lot of damage and necrosis. As you peel off the bark down below, there's less and less necrosis to the point that at the base there's very little. So it's a good indication that woody weeds and perhaps woody crops would be less affected by this technology. But this is not as perfect as I'm showing. We had significant problems midsummer, which is the fire hazard. That was a demonstration. Worst time possible. We had a field day, and then suddenly we were like trying to put off a fire. So it's pretty clear that we have 2 times of the year, at least in Oregon, when this is not ideal. One is when it's too dry. In our case, it's after July, or when it's too wet. That could be this time of the year, definitely, but it could be all the way to March. So there is a window between March and June where we can safely use this technology. And that really varies on site by site and even years. There are some years we have decent rainfall all the way to August, but that was not the case last year. It seems to be quite different in 2022. The crop safety. This is just in early stages. By the time we get everything set up to be able to do a reliable treatment, it was July. So we only did 3 applications in 2021. So far, everything looks fine, even at the highest rates. And that's based on leaf area, trunk caliper, and growth. This is a first-year crop, so likely this is the most sensitive time it will ever be to any treatment. But I do believe that before we say this is safe for sure, we need to continue that study. So far, can I say that electric weed control is a viable option in hazelnuts and perhaps in other crops? I say so far so good. It's pretty encouraging results. We have effective weed control at 2 miles an hour, which is fairly good speed compared to some tillage options that would be much slower. Initially safe to hazelnuts, and I would claim safe to the operator as well, provided that you're inside the cabin when applying. It's compatible with our production system. I've driven over some irrigation lines that did not damage it, at least a single application. So I don't see a big problem with our irrigation on the surface or any of the layout of the equipment. The biggest limitation I had in Oregon is either the wet soil or the very dry conditions. This is something that maybe an electrical engineer could help us to minimize this problem, that maybe there's something we can do to fine-tune the equipment for our conditions. The economics are to be determined, but that implement I show you, it retails about $50,000 to $60,000. It's hard to talk about prices now. Everything's going up by the minute, but I paid $50,000 in 2020. So going at 2 miles an hour, I don't think it's going to be too expensive. I'm guessing below $50 an acre, which is somewhat comparable to some of the herbicides we have available. When we have the herbicides available, this is a problem of 2022. And talking about the environmental, well, there's no chemical residue, so we don't think about, when we talk about export crops, we don't need to mention maximum residue levels when we're talking about electricity. There's no soil tillage, which is a huge improvement compared to some other alternatives. But the negative side is very hazardous, which I believe in Oregon can be circumvented by the time when you do the treatments. And that's what I had to talk about today. This is in the early stages, and I would like to acknowledge USDA for the funding, lab members for all the work. You know, we're moving heavy equipment up and down the state. It's not something I can do on my own. Oregon Hazelnut Commission for a lot of support finding growers, and then some of the collaborating growers that hosted this trial. And with that, I'm glad to take any questions you may have.
Well, thanks, Marcelo. I'm looking at the chat currently, and I'm not seeing any questions. So if folks have questions, you can take your mic off of mute and go ahead and pose your question, or if you prefer, you can also pose your questions in the chat. Marcelo, I just have a quick question. I know that sometimes it may not be all that critical how this technology works to kill the plant, but I'm wondering, it might be important in this case because I was wondering, could it explain why some plants are less or more susceptible to the technology, to the way, there might be some feature of the plant that makes it less likely to be killed using whatever method this is using to kill, or could different plants be killed by this technology differently?
Wrong. Am I? Yeah, I'm not on mute anymore. Yes, this is very important, not only for killing the weeds, but for not killing the crop. I would like the other crop I work a lot is hops, for instance. And in that case, the foliage is down the ground, so I don't have that difference in height that I'm not applying my treatment to the foliage. I don't have that luxury. I have to do it over the top. So yes, understanding what makes it more or less sensitive, it's very important. So we can optimize application rates. That's the simple idea. No, you don't spend as much diesel burning diesel to go slower if you could go faster, or many other alternatives. But I think that's very important, what it does to the plant and what's doing to the soil as well. I didn't talk about it, but in one of the studies, we're going to look into soil health, preliminary information, say high voltage moving through the soil. Does it have any impact, positive or negative or negligible? What are we talking about?
So we do have a question in the chat from Len Coop, and he asks, would your methodology work well with other orchard crops or even vineyard crops?
Yes, I suspect that most of the woody fruit trees or tree nuts would have a fairly similar tolerance to hazelnuts. Among the tree nuts, I suspect hazelnuts are the worst case scenario because of the suckers. Again, I have foliage down there. So if it's safe here, I suspect it's going to be safe to almonds and walnuts and pistachios. Vineyards, yes, there are some work from that company testing in vineyards in Europe. I forgot the country. I think it's France. And their conclusion with a slightly different setup is that it was as effective as herbicides with a lower cost. The other crops I'm most interested are, well, hops for one, and blueberries. The blueberries mostly because the roots are so shallow. The root system is down on the surface, and we are applying mulches. So that could be great or could be very bad. I don't know, but it's the other one I would say. If it's safe to blueberries, I would dare to say it's safe to blackberries and raspberries. So case by case, the crops that I don't see much hope are like cranberry. I'm just starting to work on cranberry, and that's like a mat. It would have to be a solution more like the ones we saw in row crops. But then you talk to the growers, they are small growers, and they don't want to drive over it. So what can we do?
Yeah. So this is a question from Todd Gaines. He asks, in dry conditions, could you add a water sprayer or mister in front of the electrical application to reduce fire hazard and improve conductivity?
Fire hazards, I doubt. I doubt fire hazards you can so easily avoid. But for electrical conductivity, I suspect so, because the example I was telling you from Crop Zone, I might be wrong. In one of my slides, I had a company from Germany. They are applying a proprietary solution, which I think is water and salt, some sort of salt, to improve the conductivity. So the reason why I use high voltage is because we have a natural barrier, which I believe is the cuticle of the plant. It's just like our skin, why you don't get stung by electricity as easily, but if you have wet hands, you do. Well, you're just reducing the resistance of the first barrier. That's why I believe we need the high voltage in the first place. And the amperage is likely the one doing the work, specifically heating up the plants and the electrons moving. But we don't need a lot of electricity to be lethal. In human beings, I think I saw somebody told me it's only milliamps that could be lethal. provided that it gets into you. In plants, I don't remember seeing a specific number, but I suspect that if my electrodes were into the leaf, it would take a lot less energy than on the top of on the surface of the leaf. So yeah, this is where I would like to continue this work.
Yeah. So here's the next question. Have you tried directly zapping, applying electricity to the suckers of the hazelnut plants to test the amount of damage that different ages of hazelnut trees, to test the amount of damage to different ages of hazelnut trees and watch the recovery from any damage?
I would like to. I've been doing it on my own orchard because that's not a good proposition to have to a grower, right? How many trees can I kill? I was like, well, not. So it takes time to convince people. So in that experiment that I have, there are some treatments with suckers where we are applying directly, and there are other treatments without suckers. What I'm realizing, at least last year, the contact of suckers to the electrode was fairly minimal. So it's upright. It doesn't take long until I'm not able to treat the top of it, which is good. That's likely what's going to happen in the field. The problem that I'm not being able to replicate right now is that the suckers don't come only from the base. I've seen suckers 3 to 4 foot away from the tree, and those would have a direct heat from my electrode. My long-term evaluation may not basically evaluate all the possible scenarios, which is normal. So down the road, if I have access to more orchards, this is something I would like to do. Maybe it could be a way to control suckers. We're spraying a lot to control suckers. Right. Maybe it takes some convincing to let people experiment with high voltage on their orchards, but I'll get there.
Yeah. So next question is from Mark Siemens. Is there a minimum weed height required for the system to be effective? So for instance, would it work on 3 to 4 leaf stage weeds, perhaps less than 3/4 of an inch tall?
Oh, it's touching the ground. So I don't think it has any pre-emergence activity. So the seedlings that have not emerged, I suspect they're not going to be controlled. I could be wrong. But when we did some of those studies, it was the time when knotweed was emerging. Knotweed is a prostrate knotweed, which is by the name, is a prostrate weed. And the tiny seedlings were gone. It doesn't matter how fast we were driving or what voltage. So you will get tiny seedlings. I don't think you have a minimum. It really depends on your cropping system. You know, the smaller they are, the faster you can go. But probably there are other considerations to say when you're doing something. It would be fantastic for vegetables like that stale seed bed, where you're definitely not, you irrigate, let it dry, and then you're definitely not tilling the soil.
So here's another question to method, the way the technology works to kill the plant. Have you tried or have you considered directed microwave energy as a heating source independently or in conjunction with electrical weed control?
Not in conjunction. I did see microwave as more not a commercial unit or a commercial type of weed control yet. The one that I'm aware of is coming from Australia. And looking at energy profile, I suspect it would take a lot more energy in microwave than electricity. The second problem I see with microwave or lasers, there's a commercial company doing lasers in Washington, is that the benefit of electricity is that you have a root activity. I don't call it systemic because Todd Gain is online, he's gonna correct me, but I see root activity. This thing is moving through the plant and perhaps killing tissues down below. And then the microwave doesn't have a good penetration in the soil. I know it would stay on the top surface, and I suspect the laser as well. And those would be more complicated technology. Again, everything I show you, I assemble with my technician, and I'm not a handy person. So it's fairly simple, not many moving parts. I don't know how the laser would be. When I read about lasers, they say it doesn't do well in dust and vibration and heat. Well, this is field work.
Yeah. So all of us in the West, of course, are familiar with fire, and living in fire country, this just doesn't seem like it would be viable. This is another question from the chat. Wouldn't a grower using it be liable for a fire they started that spread?
I think so. The viability, I think the value is there. It's just the application is much more limited. I would not use it in Napa Valley vineyards. You always have some dry grass, you're up in the hill. But if I go to Salinas, I'm doing a pre-planting vegetables, let's say lettuce, there's nothing to burn in there. It's just the weeds coming up. I think there is opportunity. I think almonds, Dr. Hanson and I will start working in 3 crops. He's going to be doing almonds. I don't see much fuel to burn in a well taken care almond orchard. But it goes from situation to situation. If there is a lot of fuel, they're just not a good idea.
Yeah.
But even flail mowing can start a fire in that situation.
All righty. I am not seeing any additional questions in the chat. If there are any additional questions, you can still type them in there, or you can take your mic off mute. I'm sure you can do a better job of asking your question than I've been able to do. Okay. I'm just seeing lots of thanks. Oh, here we go. All right. So here's the next question. How wide are the paddles of the system, i.e. the flaps that serve as the electrodes?
So the 2 applicators are 2 feet each one. They could be made as a single 4-foot for a 30 kilowatt generator, twice as big for the 60 kilowatt. The length of the electrode itself, I haven't measured, but I suspect it's like less than a foot or about a foot. It's about as big as my hand, it's about a foot. And there's 2 sets of those, the front and the back. This is alternate current. So I don't know if I can say this is positive and negative, but that's how they operate. And I guess the flaps, terminology here is not official, but the flaps, I guess, is the part that moves sideways. The unit I have did not come with the flaps, and I've been complaining to the manufacturer for a while. But the ones that they do have is about 2 foot wide. So on top of that fixed electrode scenario, you have the flaps on the side.
Yeah, makes sense. Okay. I think we may be winding down on questions, Marcelo. You may have weathered that storm effectively.
I appreciate the questions. That's the part why we present, right?